All right, this is the second empirical formula video, so please make sure you go back and watch the first one before this. This is how to calculate an empirical formula for a compound that is 69.8% iron and 30.2% oxygen by mass. So as in the other video, the first thing that you do is you assume a 100-gram sample. That way we can change all of our percents into grams, and we can change our grams into moles. So if I have 69.8% iron, that changes it to 69.8 grams of iron. And my 30.2% oxygen changes to 30.2 grams of oxygen. Then I use my periodic table in order to change each one of these into moles. So look on the periodic table. 1 mole of iron weighs 55.85 grams, rounded to 2 decimal places. And you know the molar mass of oxygen by now. Molar mass of oxygen is a nice even 16. So grams of iron are going to cancel out. And using my calculator, which you hopefully have in front of you, is 1.25 moles of Fe. And then my 30.2 grams of oxygen divided by 16 is going to give me 1.89 moles of oxygen. So what I need to do now is make a nice little ratio between my 1.25 moles of iron and my 1.89 moles of oxygen. So looking at these two numbers, which is the smaller of the two numbers? Because I need to get a 1 to something ratio. It's the 1.25. So if I divide both of these by 1.25, I get 1 mole of iron for every 1.5 moles of oxygen. Does that work out? Fe10 1.5? Can I have a non-whole number in an empirical formula? No, I cannot. So what do? How do I fix this? How do I maintain a 1 to 1.5 ratio but make it a whole number? Well, what is the next smallest whole number? My next smallest whole number is 2. So multiply your whole ratio by 2. Double the whole thing. This changes to a 2 to 3 ratio, which means Fe2O3 is our empirical formula. This is iron 3 oxide. So this is where we implement that last rule because we don't have a whole number in our ratio. So if you take a look at it all typed out for you, you see again we assume a 100-gram sample first, then we change our percents to grams, convert our grams into moles using the molar masses. So 69.8 grams of iron divided by 55.85 gives us that 1.25. And my 30.2 grams of oxygen divided by 16 gives us 1.89 moles. And then I set up my 1.25 to 1.89 ratio. I get 1 to 1.5. That doesn't work. So you'll see in the notes on the next slide, we have to fix that. And the way that we fix it is to get to the next lowest whole number. Try 2. If 2 doesn't work, then try 3, but it shouldn't really be much more than that. So we double our ratio. Iron 1 to 1.5 becomes Fe2O3, which is our iron 3 oxide. That ratio is now a 2 to 3, which is a whole number ratio. And you have to be in whole numbers because we can't split atoms. We're not doing nuclear chemistry here. No, siree, no hurry, Bob or Bobette. Okay, so this last example is going to ask you to figure out the empirical formula for a compound That is 31.9% potassium, 28.9% chlorine, and the remainder is oxygen. So we have some sort of KClO compound, and we're not sure what it's going to be. Okay, so what do all of these percents add up to? You got it, you know. All of the percents add up to 100. So if we subtract out that 31.9% potassium and subtract the 28.9% chlorine, go get your calculators. What is our remainder, our percent oxygen going to be? Do you know? Okay, so figure it out. Type it in. It's going to be 39.2% oxygen. Good. So now what do? We assume a 100-gram sample. Okay, now we can change all of our percents into, you guessed it, into grams. So we have our 31.9% potassium becomes 31.9 grams potassium. Our 28.9% chlorine becomes 28.9 grams chlorine, and that remaining amount, that's oxygen, 39.2% oxygen becomes 39.2 grams oxygen. Okay, follow it the same way that you have been doing for the other examples. Change all of these into moles. Okay, so potassium, 1 mole of potassium on the periodic table weighs 39.10 grams of potassium. 1 mole of chlorine weighs 35.45 grams of chlorine. And 1 mole of oxygen weighs 16. All right, so now we're cooking. All right, so let's do 31.9 grams divided by 39.10 grams, and we are going to get 0.816 moles of potassium. Let's try to keep these 3 sig figs that are given here in our 3 sig figs that are given here, okay? Next, we're going to do our chlorine, 28.9 grams chlorine divided by 35.45. Oh, hey, check this number out. Not a coincidence. It's purposeful. 0.816 moles of chlorine in here. And then 39.2 grams of oxygen divided by 16 is going to give us, ooh, this is a different number, 2.45 moles of oxygen. Okay, so this usually frightens some students because they're like, how do I take a ratio of all 3 numbers? So what you do is you do the exact same thing. 0.816 moles of potassium for every 0.816 moles of chlorine for every 2.45 moles of oxygen. So what did you do before? You divided each number by the smallest of the 3 numbers. Because in essence, what we're doing here is we're changing K.816, Cl.816, O2.45 into whole numbers. So how do we do that? Which is the smallest number? It's 0.816. So you kind of do 3 different division problems. Okay, so you got 1 mole of K for every 1 mole of Cl for every 3 moles of oxygen. Cool. So what does that turn into? K1Cl1O3. Clean that up. KClO3. Hey, I know that. That would be potassium chlorate. All right, so that's what these 3 numbers are going to reduce down to so that you get your whole number ratio. So we get, again, check and make sure that you have your 100-gram sample first. And if you have all your grams, you can either subtract from 100% or from 100 grams, either one, but you can get your missing amount of oxygen here. Change all of your grams into moles. So for potassium, it is going to be 31.9 divided by 39.1. And then for chlorine, it's going to be 28.9 grams divided by 35.45 grams. And for oxygen, it's going to be 39.2 grams divided by 16. And I take these three numbers and set them up in my ratio. And my ratio, I divide those three numbers by the smallest of the three. So what I end up getting is 1 mole of K for 1 mole of Cl for every 3 moles of O. And I get KClO3, or potassium chlorate. And that is our second and third level empirical formula problems.